Washington State University. Go Cougs!
We'll try to essentially, once we have a picture, it's easier to see. So we'll be using all these .c files, and if you look at this other screen here, the names are slightly different. So essentially, let me highlight those source code that we'll be working on. We'll start from loop-serial. It's a serial loop program, and try to parallelize it. And then we will start from a sum compute serial program and try to parallelize it. Okay, and here is another code that we'll be using, synchronization, but it's an unsafe synchronization. We'll make it safe. Okay, and there's at least one other code here in this repository, which I'll go over at the end of the workshop, but that's for your like off the class review, but I'll cover the concepts here in the workshop. It's about matrix vector multiplication. All right. Okay. So we'll be using Kamiak, and I guess all of you have access and by now logged in and got your this training module already loaded. So like I mentioned, there are really two major classes of parallel programming. These are parallel programming models: shared memory, distributed memory. So let me talk of the shared memory that I was talking about. Really, it's multi-threading. Okay, fits into this model, shared memory architectures. So what you have is basically a compute node, a single node, which could internally have multiple cores. Let's say this is core 1, core 2, core 3, and each of those cores is attached to a cache, and those caches are connected through a memory bus, and here there's a memory controller, and it's connected to a memory, a RAM, a random access memory, right? So obviously this is a larger space. It will be in the orders of maybe 128 GB or whatever your machine has, and then that connects through an IO bus to your disk, which is much larger in terabytes. All right. So essentially, as you go from the cores to the disk, the volume of memory increases, but the access speed decreases. Right. So we want the data to be as close as possible to the individual core so that the computation can be fast. So any data that the cores need to be working on should be brought ultimately to the cache and to the registers within the cores in order for you to be able to do any manipulation of those data. Okay. So what the shared memory architecture is basically saying, I might have multiple cores on a single node, but they all share the same memory, and so the same memory can be used as a shared address space. Okay. So basically, I can create a variable if this core, using one of the threads that is executing on that core, if it creates a variable on the memory, other threads which are executing on other cores of the same node can also see that variable and how it changes. Okay, so that's what I mean by shared address space. This is not a virtual memory. This is not virtual memory. This is really the DRAM, which essentially has which is where when your program initiates, you basically load all the variables, what the main function and the global, all the global variables come onto the process space. So basically, there are heaps and stacks and so on. I don't want to get into that, but essentially the memory is what you have on your laptops on the compute nodes, right? Which is like 8 GB or 16 GB, whatever you might have. That's where the program stores the data corresponding to the variable, corresponding to the programs. Does that make sense? Okay, so the key point here is multiple threads can map to a single core, in which case they have to time share. Multiple threads can also map to multiple cores, right? And those threads all get the unified vision or view of the data that's stored in the memory. Okay? So ideally, to maximize performance, we would like to map a single thread to a single core. That way, there's no need to do any time sharing. That thread has exclusive access to that core, right? So that way, there's no waiting time saying, oh, let the other thread finish, then I'll take up from where I want. The waiting needs to be dictated by the dependency of data between the threads, not by the computing resources. All right. So there is an alternate view, that's the distributed memory. So essentially these are the key points, multiple threads mapped to cores, and then those all share the same variable. So basically these threads may be executing different instructions of the same program at the same time. Okay, so I'll get on to where in the code these threads are executing shortly, very soon, but this is how the thread to the cores mapping is. The second thing that I want to show you is what is a master process and the worker threads. And so essentially when a process starts, you have only one thread executing at the start. It's what's called the master thread, okay, which is same as the parent process. Over a period of time, after some time, maybe you said I want to have two threads. I want to have two, say, additional threads, right? So which means this is maybe thread number 1, thread number 2, that spawns off the master thread. Now at this point we have 3 threads that are active, right? And one thread may independently compute, and one could finish sooner, one could finish later, and you do basically what is called a join, meaning that you wait until all the threads complete and then you complete the entire process. Okay, so a process cannot complete until all its child threads have also completed. Okay, and you can do this forking of new threads and joining of those threads multiple times in your program. Okay, so that's the shared memory architecture which we'll be using for this workshop. Yeah.
So you're saying within a process you can have these multiple threads, but the process doesn't end until they all come back.
That's right, yeah. The process is thread number 0, and it stays alive until all the other threads complete. Okay, so the alternate model is the distributed memory, where essentially you can think of it as multiple shared memories connected over a network, right? So in Kamiak, for example, we have multiple compute nodes, right? Each compute node internally is a shared memory architecture. And then those compute nodes are connected through a network backbone, an interconnect, InfiniBand, or I guess it's InfiniBand. And so here, what happens is you can run processes, okay, on individual cores, and those processes, because each process has its own address space, one process cannot see the other process's data, and vice versa. So which means they don't share the address space. Okay, this actually complicates the programming process, right? So I can't see your data, which means I have to ask you for your data. I have to interrupt you and say, give me your data. That's communication, and that communication needs to happen over this network interconnect, and for which one of the main choices that we have is MPI. Okay, some of you have already probably written or dealt with MPI programs. Okay, so the challenges, however, in designing a parallel algorithm for distributed memory is very different from shared memory machines. Okay, all right. So for distributed memory machines, essentially sometimes we call them simply clusters, and nodes refer to those individual shared memory boxes, and cores are referred to the individual cores that are inside a node, right? So you want to first understand how many cores does each node have and how many nodes are there in my cluster. That product will give me the total number of processors or cores in my system, correct? And then you also have to look at from the memory point of view, how much memory does each node have? That's the aggregate memory, the sum of it, right, is what I have at my disposal to use for any given process, for any given MPI job. Okay, so so that's about the architectures, and basically it's the parallel programming models. The other concept that I want to touch upon is how do you how do you manage your threads or your processes? What part of your code they are executing simultaneously, what part of the data they are looking at concurrently. Okay, so for that there is a simple classification here. Basically you write one program. It's what's called the single program model. Okay, so we won't write one code for thread number 1, one code for thread number 2, and so on, right? We'll write a single program. Internally in that program, we can spawn multiple threads, right? And essentially, single instruction model basically means that you may have multiple threads executing concurrently, but they all have to be executing exactly the same line of code at any given point of time. That's single instruction model. Multiple instruction model means all the threads are executing concurrently, but each of them may be executing a different line of code in your program. There is no need to synchronize on which line of code each one is executing. So we get that flexibility. Okay. There is also a notion of single data, multiple data. Single data hardly no one uses. So I'll just talk about multiple data. Multiple data really means that all the threads may be executing concurrently, and each of the threads, however, may be looking at different pieces of data. Okay, so they need not operate on exactly the same variable or same piece of data. So this is abbreviated as essentially single instruction multiple data model, or multiple instruction multiple data model, SIMD or MIMD. SIMD is essentially, maybe I have a picture here, that's good. Yeah, so let me explain with this. So SIMD is really, this is your single program, and all the threads must be executing the same line of code, but they are looking at different pieces of data. So if you, for example, code for a GPU, which is like a graphic processing unit, you will be using SIMD processing. Okay, any vectorized processors, they follow the SIMD programming model. Okay. On the other hand, multiple instruction, multiple data is that you have a single program, right? And threads can be executing different lines of code at the same time, and they may be looking at different pieces of data at the same time. You give maximum flexibility on what they can do, right? So this is what we will do today. In OpenMP multi-threading, it falls in multiple instruction, multiple data model. Okay, which also means threads may be moving at different rates in your program. One thread may move faster, another thread may be much slower because it's working on different lines of code that may take more time, right? Then we have to worry about load balancing and so on. Okay. So if there are some basic terms or techniques, I should say, that are used in order to parallelize a program. How do you write, let's say you have a serial code and you're trying to parallelize it. We want to identify certain characteristics of the underlying method before we start parallelizing it. Okay, so one is we want to make sure how to partition either the tasks or the data. We have to come up with a way to logically partition it ahead of time in some cases and say this is how the parallel execution will happen. It's like a plan, right? So for that you have to say, okay, threads, this one thread will take charge of the first 5 iterations, the next thread will take charge of the next 5 iterations, and so on, right? So that's like partitioning. Okay. The other thing is communication, and communication is something that is more relevant to distributed memory computing, not for shared memory. If you're doing MPI, you'll be doing communication. Okay, for OpenMP there is no communication, but communication is you should think of it as coordination, right? So communication, you communicate only if you need to. In any parallel algorithm design, you want to communicate to the least extent possible, right? Communication is a waste of time, it's an overhead. Processor should be doing computing, not communication. The moment people start talking to one another, they are wasting time. That's the view of a parallel programmer, right? So communication could happen in different ways. You can say, I'm waiting for your piece of data, so I'm not doing anything else. Or I can send a message saying, please give me a data and I'll continue working with whatever I was doing, and then when the data arrives, I'll work on that, right? So there are different ways to really write efficient communication, avoiding communication masking codes. Okay, so we won't go into any of those today, because those are challenges that are primarily associated with distributed memory programs. Okay, aggregation or agglomeration. This is like essentially you're trying to combine the results obtained from different tasks or different threads in a logical manner. We will see one of those such technique called reduction today. Okay, so essentially it gives you a way to aggregate results or merge results coming from different concurrent executions. Mapping is, another concept. Essentially, how you can, mapping has multiple interpretation. Essentially, you can break the task into multiple composite tasks, or you can try to understand which part of the data needs to be or computation needs to be mapped to which thread. It can also be interpreted as basically masking. If I can do some prefetches and so on. Okay,